Hello, fellow Biz 102 students. Welcome to Biochemistry with Justin. Today we will be covering 4 types of inhibition: competitive, pure non-competitive, mixed, and uncompetitive. First, let's start off with some key vocabulary. First, the Km is the Michaelis-Menten dissociation constant, and it is the concentration of S at which the velocity is 1/2 Vmax. Next, we have Ki, and Ki is the dissociation constant of the inhibitor when it is bound to E only. Next, we have Ki prime, which is the dissociation constant of the inhibitor when it is bonded to the ES or ternary complex. And lastly, we have Kmap or Km apparent, which is the apparent Km. First, we'll begin with competitive inhibition. I and S compete for the same active site. In addition, at high substrate concentration, I, the inhibitor, will be kicked out, which means that inhibition is overcome. Since I and S compete for the same active site, the inhibitor affects the Km. In other words, it affects the affinity. A Km apparent that is high means that there's a lower affinity. Lastly, Vmax does not change. It just takes more time to get there when the inhibitor is present. Now we're going to go over the equation. Remember that we always start with the Michaelis-Menten equation, V equals Vmax times S all over Km plus substrate concentration. Now we're going to take into account the fact that Km changes by a factor of 1 plus I over Ki when we're rewriting our Michaelis-Menten equation. To get this equation in the Lineweaver-Burke form, we're going to take the inverse of V by doing the reciprocal, 1 over V. Then, simplifying this equation more, we can write 1 over V as Km over Vmax times 1 plus I over Ki times 1 over the substrate plus 1 over Vmax. Similarly, we can rewrite our basic Michaelis-Menten equation in the Lineweaver-Burke format. Notice that the equation is y equals mx plus b. In other words, the equation is similar to our linear format, which now we can draw the graph. And we have on the x-axis 1 over substrate, and on the y-axis 1 over v. And we're going to add in our line in which we have no inhibitor present. If inhibition, what stays the same? The answer is Vmax. So when we draw in our line with the inhibitor, we know that it will cross through the y-axis at the same V. We can then see that the slope is Km over Vmax times 1 plus I over Ki, and now we can also go ahead and label our points, and so that's negative 1 over Km there. There is 1 over Vmax, and similarly for our inhibitor, that point is negative 1 over Kmap, and then we also see that the Vmax stays the same. Now we can move on to our second type of inhibition, pure non-competitive inhibition. So in pure noncompetitive inhibition, we know that I binds at a site that is different from where S binds. So it does not bind at the active site, but in its own unique site away from S. Second, we know that the binding of I by the enzyme has no effect on the binding of S by the enzyme. So in other words, I binding does not affect S binding. Third, we know that inhibition cannot be overcome by adding more S, as it was in the case of competitive. We also know that the binding of the inhibitor in pure noncompetitive does not affect Km. However, Vmax is affected, and it changes by a factor of 1 plus I over Ki. Okay, again, just for reference, we're going to write down the equation of our general Michaelis-Menten, and that is V equals Vmax times S all over Km plus S. We can then go ahead and modify our equation for velocity because we know that it is changing by a factor of 1 plus I over Ki. So our new equation under pure noncompetitive becomes V equals S Vmax, don't forget the S times Vmax over 1 plus I over Ki all over Km plus S. We can then take the reciprocal to get it in our Lineweaver-Burke plot form, and so we get Km plus S all over S times Vmax over 1 plus I over Ki. We can then simplify this more with some basic algebra until we finally get it in our recognizable form. 1 over V equals Km over Vmax times 1 plus I over Ki times 1 over S plus 1 over Vmax times 1 plus I over Ki. And recognize that this is our same equation for the linear form y equals mx plus b. Okay, now we can go ahead and draw in our graph. And so on the x-axis we have our 1 over s, and on the y-axis 1 over v. We can also draw in our line with no inhibitor. And what changes in the case of pure noncompetitive inhibition? Actually, what stays the same, sorry. That's right, Km stays the same. So when we draw in our line with the inhibitor, we know that it will have the same Km, but a different V. In addition, we can go ahead and label our points. So there is -1 over Km, which is the same for both, as we know. And there is 1 over Vmax. However, the Vmax for the inhibitor is different, so we'll call this 1 over Vmax apparent. Okay, so now we're going to switch over to one of the more challenging types of inhibition, which is mixed noncompetitive inhibition. And so, there are some key things that you should know about mixed noncompetitive. The first is that the binding of the inhibitor by the enzyme influences the binding of the substrate by the enzyme. And so this is actually thought to be due to the binding sites of the inhibitor and substrate being different but still located near one another. And the second thing is that I causes a conformational change which affects the way that the enzyme binds to the substrate. Next, we should know that Km and Vmax are both changing. I know I wrote Ki there, but don't worry, I'll fix that. So Km and Vmax are both changing. And so we can actually think of mixed inhibition as sort of a combination of competitive and uncompetitive inhibition. And so this actually alters how we interpret the equation and figure out which factors are changing by 1 plus I over Ki, which we will actually see once we derive the equation. And let's not forget our standard Michaelis-Menten equation as our foundation for deriving the next equation. Okay, so we know that in mixed noncompetitive, Vmax changes by a factor of 1 plus I over Ki. And so that means that our V apparent is given by Vmax over 1 plus I over Ki. However, due to the formation of the ternary complex, we have a special form of Kmap. Okay, so before we knew that Kmap or Km would change by a factor of 1 plus I over Ki. We got that, which causes Km to go up. But when we have our weird mixed noncompetitive situation with our ternary complex, a different principle comes in, and that principle is called Le Chatelier's principle, which you may remember from the Chem 2 series. So as we remove ESI, so as I forms with the ES complex and we get the ternary complex, the reaction is shifted to the right. So when the reaction shifted to the right, that inspires more S to bond to the E faster than usual. So in a way, an inhibitor in a ternary complex actually helps. Okay, so now we can go ahead and set up that new weird Km, or Kmap in this case. So that was our old one, Km times 1 plus I over Ki, but now we have to have Km times 1 plus I over Ki all over 1 plus I over Ki prime. So in other words, we're saying that we must add the denominator because the ternary complex can actually help the formation of the enzyme substrate. And so depending on Ki and Ki prime, Kmap may actually be bigger. So that means that you have a better inhibitor, or it may be smaller, which means that the inhibitor is not as inhibitory, and so it'll be less effective. Okay, so I'm just going to make some adjustments here, and we're going to go over our new weird equation. Okay, so don't forget our original Michaelis-Menten equation. And so now we're going to incorporate both the change in Km and the change in Vmax to our new equation. So there's our old Michaelis-Menten equation as our base, and now we're going to write the new one. So V equals Vmax over 1 plus I over Ki prime times S all over Km times 1 plus I over Ki, no prime, which is then over 1 plus I over Ki prime, plus substrate. Okay? And so now we're going to go ahead and multiply both the numerator and denominator by 1 plus I over Ki prime, just so we can simplify a bit. And now we get Vmax times S all over Km times 1 plus I over Ki plus substrate times 1 plus I over Ki prime. And so rearranging that into our Lineweaver-Burke form, we get the following. Okay, so doing a little bit more readjusting, we can now go ahead and get started with our graphs for mixed non-competitive inhibition. And so on this graph, we're going to start with our non-inhibitor line case, and then we're going to draw in an inhibitor. And so here are axes, and we can also label points such as 1 over Vmax and negative 1 over Km. And then for the inhibitor, we will have negative 1 over Kmap, as well as negative 1 over Vmax times 1 plus I over Ki prime. And you can figure that out using the equation y equals mx plus b and solve the y-intercept by making x, or 1 over s in this case, 0. Okay? And so you should also know that negative 1 over Kmap has a specific definition, and it is defined as negative 1 times 1 plus I over Ki prime all over Km times 1 plus I over Ki. And that comes from the equation you just solve for K. And so let's say we want to figure out whether Ki is bigger or smaller than Ki prime. And so from the graph, we can see that Km is actually smaller than Kmap. And that is because if Km is smaller, that means that negative 1 over Km will be larger, and Kmap is bigger, so negative 1 over Kmap in blue is smaller. Okay? And so using our equation for Kmap, we have Km times 1 plus I over Ki all over 1 plus I over Ki prime. And so we see that Kmap is larger. So in order to have a large Kmap, you have to have a large numerator and this small denominator so that Kmap in the end is large. And this only happens when Ki prime is greater than Ki. Because if Ki is really big, then the denominator is small, and if Ki prime is really big, denominator is small, and when Ki is small, the numerator is really large. So overall, the effect is a large Kmap, which is what we see in the graph. And now we can do the same for the second case. So you have no inhibitor, and the line will extend down as we know. And then this is negative 1 over Kmap, and this is 1 over Vmax times 1 plus I over Ki prime, and that is 1 over Vmax, and this is negative 1 over Km for the non-inhibitor case. And so we know, as we found before, negative 1 over Kmap is equal to negative 1 plus I over Ki all over Km times 1 plus I over Ki. I'm sorry, I should have said Ki prime in the numerator. And so let's say we also want to figure out, is Ki bigger or smaller than Ki prime? And again, we see from the graph that Km is larger than Kmap, due to the fact that negative 1 over Km, the inverse, is smaller than negative 1 over Kmap. So Km is greater than Kmap, and we know that Kmap is equal to Km times 1 plus I over Ki, which is over 1 plus I over Ki prime. And so we have a small Kmap, which means that you have to have small over large. And the only way that that happens is if the numerator is small, so Ki must be large, and the denominator is large, so Ki prime must be small. So Ki prime is less than Ki. Alright, so good job, you got through. Okay, so now we're going to finish up with our last type of inhibition, which is uncompetitive inhibition. And so, in uncompetitive inhibition, the inhibitor only binds with the ternary complex. So I plus ES gives you ESI. In addition, the ternary complex does not lead to product formation. Finally, the inhibitor affects both Vmax and Km, but they are affected proportionally, which you will soon see. Okay, so now let's figure out those equations. We know that V changes by a factor of 1 plus I over Ki. So Vmax decreases by that factor. In addition, we know that Km changes by a factor of 1 plus I over Ki prime. Also, don't forget our buddy, the original Michaelis-Menten equation. Okay, and now we can write the new form of the equation with Vmax changed by its factor of 1 plus I over Ki prime, as well as Km changed by 1 plus I over Ki prime. And then don't forget your substrates. And so we can simplify this to Vmax over Km plus S times 1 plus I over Ki prime. And so we can then take the reciprocal to get it in our Lineweaver-Burke form. And this simplifies to Km over Vmax times 1 over S plus 1 over Vmax times 1 plus I over Ki prime. Don't forget, this still follows our same y equals mx plus b linear equation. And we see that the slope is the same as our Michaelis-Menten without an inhibitor. And so now we can go ahead and graph this out. And so here are the axes. And now we're going to draw our line without an inhibitor. So this is no inhibitor. And then we could also draw in our line with the inhibitor, which is supposed to be parallel. Sorry, my line's kind of squiggly there. But it has the same slope as the non-inhibited case. And so we're just labeling our points. This is negative 1 over Vmax apparent. Sorry, not negative, positive. And this is 1 over Vmax. Alright, thanks for watching and good luck on your exams!